Okay, so hello everyone. Today we have the pleasure to have Dr. Alex Drlica-Wagner from Fermilab, and he's going to talk about fundamental physics with the smallest galaxies. So thank you a lot for accepting this invitation. So please, can start.
Great, thanks. So I'm just going to say a little bit about what I think has been a very exciting field of research, especially over the last year and a half with the Dark Energy Survey. And so on my opening slide, this is the 4-meter Blanco telescope at CTIO in the foreground, and then in the sky, obviously photoshopped in there, is the Fermi Large Area Telescope, which is a gamma ray satellite telescope, which I'll talk a little bit more about in the second half of the talk. So just before I get really into things, I thought it'd be worth just emphasizing how large of a part the DES Brazil group has played in all of the analyses that I'm going to be talking about here. Really, the Brazil group has been a very strong contributor to all of the Milky Way science in DES, and I just wanted to recognize that up front. And I'm sure that locally, if you have questions about any of the things that I'm going to be talking about, you can find very knowledgeable people in Brazil who'd be very interested to talk to you about any of this stuff. So just as an overview of what I'm going to talk about, I'm going to give a very brief introduction to dwarf galaxies, talk a little bit about how we find new dwarf galaxies and some of the new dwarf galaxies that have been found in DES. I'll give some very brief case studies on some of the things that we can learn from these new dwarf galaxies. Then I'll talk at some extent about why dwarf galaxies are specifically important when we talk about searches for particle dark matter and trying to understand the fundamental and microscopic nature of the dark matter that dominates the mass of the universe. And then I'll end by just giving you a brief glimpse at some of the future things that are coming in this field. So starting with an introduction to dwarf galaxies. Here's a picture. This is a cartoon that was produced by James Bullock and Marla Gea and others. And it was accurate up until about 2014. It's a picture of the local neighborhood around our Milky Way galaxy. And what you can see right away is that our galaxy is surrounded by many small satellite galaxies. As of 2014, we knew of about 24 of these small satellite galaxies. They're relatively close to Earth, on the order of 10 to the 5 to 10 to the 6 light years, or 25 kiloparsecs up to 300 kiloparsecs. They have luminosities that span a very wide range, from sort of 10 million solar luminosities in the brightest dwarf galaxies. So this is Fornax. This is the brightest, with exception of the LMC and SMC, of course, down to only several thousand solar luminosities in some of the ultra-faint dwarf galaxies that have been discovered recently. So one of the reasons that these dwarf galaxies are so interesting is that they're some of the most dark matter dominated objects that we know about. So this means that they're relatively astrophysically simple. They have very few baryons, very few stars, and the stars really can be thought of as a tracer for the dark matter potential. And so this allows us to use dwarf galaxies really as a probe of dark matter and fundamental physics at the smallest scales. So just a plot that summarizes that last point here. This is from paper by Wolf et al. In 2010. What you see on the x-axis is I-band luminosity, so essentially the brightness of objects. And this is spanning over several orders of magnitude in luminosity, with the dimmest objects on the left and the brightest objects, which are clusters of galaxies, on the right. And then on the y-axis, what you see is the mass-to-light ratio. So this is essentially the derived dynamical mass from various kinematic measures compared to the luminous mass measured from the number of stars in the luminosity. What you can see is that there's this interesting U-shaped character to the mass-to-light ratio of objects that peaks both at very low masses, so these are the dwarf galaxies, specifically the ultra-faint dwarf galaxies around the Milky Way, and then peaks at very high masses with clusters of galaxies. And so what we're talking about here is objects that can have hundreds to thousands of times more matter than they have luminous matter. So they're very much dark matter dominated. And so another way to think of this, a way that a cosmologist or a simulator would think of this, is that the Milky Way actually lives in this very massive dark matter halo. And the dark matter halo is not completely smooth. You actually have small clumps and overdensities of dark matter that have been accreted onto the halo as a part of galaxy formation. So the Milky Way disk is actually a rather small component of this much larger dark matter halo. So the idea is that the Milky Way resides in the center of this massive dark matter halo, and in the centers of these smaller dark matter substructures are dwarf galaxies. And dwarf galaxies really offer one of the few observational ways that we can actually probe this scenario of a very highly hierarchically structured Milky Way dark matter halo. And the idea here is that we can then use dwarf galaxies to tie into galaxy formation, since we have extensive numerical simulations that show that larger dark matter halos form from the accretion of smaller halos. These dwarf galaxies are really tracing the smallest dark matter halos that were formed primordially and have now been accreted onto the Milky Way. And so the idea is that these dwarf galaxies are really tracers of the local dark matter distribution. So ultrafaint galaxies, because they have so few stars, so little astrophysical activity, and so much dark matter, are really the excellent probes of dark matter physics. And in fact, a lot of fundamental physics related to the formation of galaxies and stars. So ultrafaint galaxies are the most numerous, the most ancient, the most chemically pristine, and the most dark matter dominated galaxies that we know of. And this allows them to be used to probe the epoch of reionization. It was actually these very small galaxies, similar in size to the Milky Way satellites that we know of, that are essential for the reionization of the universe. They also allow you to probe the origin of heavy elements, and I'll talk about this a bit more later on. Essentially, dwarf galaxies are self-contained systems where the heavy elements that they produce are gravitationally bound to the system and captured in the system. So you can actually look at the integrated history of heavy element formation in these satellites. And then additionally, because they are so dark matter dominated, dwarf galaxies are actually excellent probes for understanding the fundamental nature of dark matter. So to go just a bit deeper into this, one of the features of dwarf galaxies that makes them very special, as I mentioned before, that the elements that are produced in them are often gravitationally captured and bound within the dwarf galaxy, so you can actually see the integrated history of heavy element formation. So there are currently there are several hypotheses for how rare R process, so rapid neutron capture elements, are produced. One is that they would be produced in supernova in small fractions per supernova, and another is that they would be formed in very rare events such as neutron star mergers, where you would produce many more of these R process elements, but the events that produce them would be much rarer. And dwarf galaxies actually offer an opportunity to try and distinguish between these two scenarios. With relation to reionization of the universe, you can see on this plot here, this is the integrated ionizing radiation as a function. This is of the mass of the galaxies, and what you can see is that actually, as you move farther to the right on this plot, you're moving to less and less massive galaxies, but you're seeing that they're actually becoming a larger and larger contribution to the UV luminosity function at the epoch of reionization. What you can also see from this plot is that some of the most sensitive telescopes that we have both presently and in the near future, for example, JWST, are not going to be able to access these satellites directly, to directly image them. And so by understanding the characteristics of these galaxies in the local universe, that may provide one of the best probes that we have for understanding how these galaxies behaved during the epoch of reionization. And then finally, because dwarf galaxies are so dark matter dominated, they are really excellent probes of the microscopic characteristics of dark matter. So one issue that's been around for several decades and was recognized in the late 90s was that numerical simulations predict that there should be several tens of thousands of dark matter subhalos bound to the Milky Way halo. However, the number of dwarf galaxies that we see, at least as of 2014, was only several dozen. And so this causes an order of least discrepancy between the number of satellites that we believe to be inhabiting dark matter subhalos and the number of dark matter subhalos that we believe exist. So a lot of work has been done on this over the last few decades, and this tension has been significantly relaxed from a better understanding of how galaxies actually form in dark matter subhalos and a better understanding of the selection functions that go into our surveys for finding dwarf galaxies. However, at present, there's still an order of magnitude discrepancy between the number of satellites that we know of and the number of satellites that we expect to inhabit the local volume. Another open issue for sort of cold dark matter scenarios is the central density problem, or also known as the core cusp problem or the too big to fail problem. And this is succinctly summarized as a discrepancy between the observed central masses of dwarf satellite galaxies and the predicted central densities from numerical simulations. And the discrepancy is such that the observed satellites are less dense than the predictions from numerical simulations. And so there have been several solutions to this proposed. For example, there are astrophysical situations where supernova feedback or baryons could stir up the dark matter profile and actually decrease the density in the central regions. Additionally, people have come up with more I want to say extreme, but they're also somewhat well-motivated ideas for modifications to dark matter. For example, that dark matter particles could be self-interacting, and this self-interaction could then disrupt the formation of very peaked density profiles in dwarf galaxies. So again, this is a discrepancy that we see between simulations and observations, and at this point, we're really observation limited in that the number of satellite galaxies that we see is still relatively small, and so the significance of this discrepancy is hard to quantify. So the idea here is that as we move to lower and lower luminosity dwarf galaxies, these dwarf galaxies become more and more dark matter dominated, which makes them cleaner probes of fundamental physics. And so if we want to try and address these questions in fundamental physics, what we really want to do is search for fainter and more dark matter dominated galaxies. And in order to do that, we really need more sensitive instruments. So that brings me to the next section of the talk, which is discussing how we actually find new dwarf galaxies around the Milky Way. So this is a picture that was taken from the site of DES, from CTIO in Chile, looking out at the night sky, and immediately you can see three distinct stellar overdensities here. The largest one off to the left-hand side of the screen is the swath of the Milky Way plain, but then directly over the Blanco dome, you can see two smaller resolved stellar overdensities, and these are the large and small Magellanic clouds, which are, of course, naked eye visible from a dark sky location in the southern hemisphere. So at 0th order, the first dwarf galaxies, the first satellites of the Milky Way, are easy to find without any technology. As telescopes improved, the number of dwarf galaxies further increased. So this is one of the first non-LMC, non-SMC Milky Way satellites that was discovered in the late 1930s. This is the Sculptor dwarf galaxy, and it was discovered on photographic plates with a 24-inch telescope. And the 2 points that I'd like to make on this slide are that that when you're searching for dwarf galaxies, you essentially have four different probes or 4 different parameters that you can use to try and distinguish the dwarf galaxy from the background stellar density. And these are the right ascension and declination of the stars, and then the colors and brightnesses in 2 photometric filters. So on the left-hand plot, what you can see is that the Sculptor dwarf is a clear and distinct stellar overdensity in RA and DEC. And on the right-hand plot, you can see that the stars in this overdensity follow a distinct isochrone in color magnitude space, which is representative of an old and metal-poor stellar population. And so by combining these 2 pieces of information, you can actually increase your sensitivity to discover dwarf galaxies. So here's a picture of what Sculptor looks like when imaged with a 1.2 meter telescope, photographic plates, and this is part of the Digital Sky Survey. So as you can see, as the technology improves, as the sensitivity of our detectors improves, objects that were originally very difficult to find become very easy. So over the most of the last century, our discovery of dwarf galaxies came in sets of 1s and 2s as people gradually surveyed the entire sky with photographic plates. In the early 2000s, with the advent of the Sloan Digital Sky Survey, digital photometry and large data sets of stellar photometry and astrometry became available, and this allowed for more complicated statistical techniques for searching for dwarf galaxies. So instead of hand scanning a photographic plate, you could now develop an algorithm to algorithmically search large data sets and large areas of sky for very faint satellites. And so the conventional algorithm that was applied in the SDSS era was to start with a stellar density over a field in RA and DEC, and to these stars you would then apply an isochrone filter which would select stars that were specifically consistent with a old and metal-poor stellar population. When you applied this filter to the stellar field, you see that you greatly decrease the number of stars that pass the filter. So this is the middle panel of the lower plot. And you can now start to resolve that there's actually an overdensity of stars in the lower right quadrant of this panel. If you then apply a spatial kernel to smooth the stellar density, you can see that this excess becomes much more obvious. And in fact, this is the Ursa Major dwarf galaxy that was found in SDSS. So with SDSS, with the digital imaging and these additional statistical techniques, we are now able to move from finding dwarf galaxies that look like Sculptor to dwarf galaxies that look more like this. So this is Segue 1. And if you can't see anything here, it's not an accident. This is actually a very difficult, one of the faintest dwarf galaxies that we know of. And it was picked up with the statistical technique that I mentioned before, but in order to confirm that this is really a gravitationally bound system, you need spectroscopy to measure the radial velocities of the stars in this field. And what you do what happens when you take those radial velocities is you find that there's a distinct peak in radial velocity at about 200 kilometers per second, where all of these stars are moving through space together and are physically bound. So from the radial velocities, you're able to determine that this is a physically bound system. And additionally, from the dispersion in these radial velocities, you're able to get a measure of the mass of this system. And from that mass, you can then derive a dark matter content. And so this is the procedure that's used to determine that Segue 1 is one of the most dark matter dominated objects that we know of. So Segue 1 has a mass to light ratio of nearly 1,000. So with the Sloan Digital Sky Survey, we were able to essentially double the number of dwarf galaxies that were known to surround the Milky Way. However, the SDSS only predominantly covers the northern galactic hemisphere, and you can see that there's a strong bias towards the density of dwarf galaxies correlated with the Sloan footprint. Essentially, the remainder of the sky that was outside the Sloan footprint had not been surveyed with adequate depth to be able to discover ultra-faint dwarf galaxies such as those that were discovered with Sloan. So this brings us to the Dark Energy Survey, which I think many of you are very familiar with already. DES is composed of a 570 megapixel camera, DECam, which is mounted on the 4-meter Blanco telescope in Chile. DECam has a 3 square degree field of view and a 20-second readout time, which really makes it one of the best survey instruments in the world currently. So you're able to survey large areas of sky very quickly, and because you're mounted on a fairly large 4-meter telescope, you're able to go fairly deep with each image. So the single image depth of a DECam exposure in G or R band filters is of order magnitude 23. And so this is already, with a single exposure, deeper than you were going with SDSS. And the survey strategy for the Dark Energy Survey is to take 10 exposures over each field within a 5,000 square degree footprint. And so from this, you're going to get almost at least 1.5 magnitudes deeper than Sloan. So with this increased sensitivity also comes some increased issues. So as you go to fainter and fainter magnitudes, galaxies, background galaxies, become very difficult to distinguish from stars based on their morphology alone. And so your stellar distribution ends up being more contaminated with these non-stellar objects. And so in order to deal with this added source contamination, we've developed a number of different search techniques which simultaneously utilize both the spatial distribution of stars and the spectral distribution of stars, in addition to a parameterization of the survey sensitivity in order to increase our sensitivity to resolve stellar overdensities that look like dwarf galaxies. So these are old and metal poor resolved stellar overdensities. So because the likelihood analysis simultaneously combines the spatial distribution of objects and a spectral model, it allows you to naturally derive a membership probability for each star in your photometric catalog using just the photometry alone. And because you're finding fainter and fainter objects, follow-up spectroscopy is becoming harder and harder because you're having to go fainter and fainter in your spectroscopy to confirm membership of these stars. So when you target your spectroscopy, it's very important that you target it accurately. And one important feature of this likelihood-based search technique is that it allows you to target spectroscopy accurately. So while the likelihood analysis technique is very nice and very powerful, really the most important part of DES when it comes to dwarf galaxy finding is just the fact that it's so much deeper than previous surveys. So this is a very first look at the stellar density without any isochrone filter over an area of the year 1 DES footprint. And so this plot was generated in January of 2015, right after the year 1 data were released to the collaboration, without any significant pre-processing at all. And what you can see here are, this is a map of stellar density. So in the lower left corner, you see the stellar population from the LMC bleeding into the survey footprint. You also see a number of known stellar overdensities. Most of these are globular clusters associated with the LMC or the Milky Way. One of them is a dwarf galaxy, Phoenix, that is outside the virial radius of the Milky Way. But then you also see a number of overdensities marked with question marks that had not been previously identified before. And the sensitivity of DES is such that these overdensities are just naked eye visible once you make a simple plot of stellar density. So the most significant of these objects, when you look at the DES imaging, looks like this. And so this is Reticulum 2. Again, it's difficult to see this object with the naked eye. Part of the reason for that is that your eye is drawn to the brightest stars in the field, and those are actually all foreground Milky Way stars. And it's actually the faint blue stars that are the ones that belong to the dwarf galaxy. So if you run the likelihood characterization procedure on this stellar field, what you find is that you identify several hundred stars associated in the DES photometry that are associated with this dwarf galaxy. You can then go and follow this up spectroscopically, and indeed you find that these stars are gravitationally bound and moving through the Milky Way neighborhood with a line 60 kilometers. So this jump in improvement that's coming from the fact that you now have a 4-meter telescope and the sensitive dark energy camera mounted on it. So moving back to the dwarf discovery timeline, so our 1s and 2s of dwarf galaxy discoveries that were spanning most of the 20th century undergo a strong increase with the beginning of SDSS and the statistical techniques that were applied to that. After SDSS was largely completed, covering its survey area, there's a gap of about 5 years before the dark energy camera was installed. And in the last year and a half, since the beginning of 2015, we've now seen another drastic increase in the number of dwarf galaxy candidates. And this is coming almost entirely from the increased sensitivity of our instruments. And so in the inset here, you can see there are 2 distinct increases in dwarf galaxy candidates. These are associated with the year 1 and year 2 data from the dark energy survey. In addition, there are a number of other ongoing surveys, for example, the VST Atlas survey, PanSTARRS, and even some small number of dwarf galaxy candidates that were found in deeper searches on the SDSS data that have also contributed to the drastic increase in the number of Milky Way satellites that have been discovered. So from this plot, you'll notice that the most recent satellites are split into 2 different groups. The filled circles are satellites that have been spectroscopically confirmed to be dark matter-dominated dwarf galaxies, while the open circles are Milky Way satellites that are consistent photometrically with being dwarf galaxies, but have not yet had radial velocities determined. And so to plot now the distribution of satellites in galactic coordinates with the dwarfs that were discovered pre-DES or pre-2015 in blue. So these are the classical dwarf galaxies and the SDSS dwarfs. And then in red, the red outline shows the outline of the DES footprint. The red markers show the dwarf galaxies and dwarf galaxy candidates discovered in DES. And the green markers show dwarf galaxy and dwarf galaxy candidates discovered with other surveys since 2015. And what you can see is that we're now starting to make strong inroads into the region of the southern sky that had not been previously explored at the depth of Sloan. So I mentioned before that what we're discovering now are many systems that are photometrically consistent with being dwarf galaxies but have not yet been spectroscopically confirmed. One of the indicators that these systems are very likely to be dwarf galaxies comes from plotting them in the plane of absolute magnitude versus half-light radius. So this is brightness versus physical size. And what you find here is that the blue markers, which are local group galaxies that were known previous to DES, follow this locus of in size luminosity space where they are consistently larger at a given size, consistently larger at a given luminosity than their counterpart globular clusters. And so globular clusters, which are known to also populate the region around the Milky Way galaxy, are essentially devoid of dark matter. And so we believe them to be a separate and physically distinct population of objects. And what you can see is that the objects that DES are finding are much more consistent with the locus of dwarf galaxies than they are with globular clusters. So just to emphasize again, what it takes to turn one of these open circles into a closed circle is that it takes about a night of observing on a 6.5 meter telescope or larger in order to get radial velocities for of order a dozen stars, which can then be used to determine a velocity dispersion and a mass to light ratio for one of these satellite galaxy candidates. So we've been working furiously to do this over the last year, but as many of you are likely aware, the weather has not been so great in Chile this year, and we haven't gotten as far as a community as we would have liked to in the last year. However, there have been a handful of dwarf galaxies that have been spectroscopically confirmed, and this is just a collage of plots from some of those papers where you can see again that what you're looking for is an association of gravitationally bound stars from which you can then measure a velocity dispersion and an enclosed mass. And just an indicator of how preliminary these data sets are, you can see that many of these papers are drawing conclusions from less than a dozen stars that have spectroscopically determined velocities. So now moving on to just a few of the interesting features of some of our newest Milky Way neighbors. One of them is that the DES dwarf galaxies are completely, or dwarf galaxies and dwarf galaxy candidates are completely consistent with the previous population of known dwarf spheroidals when you look at the gas mass and the fact that there is no appreciable gas emission, H1 emission from gas associated with these candidates. And this is interesting because there's a threshold, there appears to be a threshold at about 300 kiloparsecs where satellite galaxies go from being gas-poor dwarfs to being much more gas-rich dwarfs. The exceptions to this trend are the LMC and SMC, which are much more massive than many of the dwarf galaxies that we've been discovering here, and are also believed to be on their first infall into the Milky Way. Another very interesting study that you can do on one of the dwarf galaxies that was found in DES is to try and constrain the type of dark matter that is present. So one hypothesis was that dark matter could come in the form of massive compact halo objects, or MACHOS. And this scenario has received some amount of recent interest because of the LIGO discovery of 30 solar mass black holes. So there have been numerous studies searching for the indications of MACHO dark matter, predominantly from looking for microlensing events against background stellar distributions. And these were able to constrain the mass of the MACHO and the fraction of dark matter that it can compose at MACHO masses of less than about 10 solar masses. At higher MACHO masses, upwards of 1,000 solar masses, the stability of wide binary systems is also very sensitive to the existence of MACHO objects. But as was noted out, there's this hole between the microlensing searches and the wide binary analyses where MACHOs are not currently constrained. And interestingly, the 30 solar mass black holes reside just on the boundary of this gap. And so what Brandt did in a paper looking at analyzing a star cluster, a single solitary star cluster that was found in one of the most distant dwarf galaxies discovered by DES, was to make an argument based on the fact that if dark matter were to be composed of MACHOs with masses in the range of 10 up to 1,000 solar masses, then these MACHOs would dynamically heat this globular cluster, this star cluster, and actually lead to its disruption. So the very existence of this star cluster leads to the conclusion that, or places a strong constraint on the existence of MACHO dark matter. Another very interesting study that's been done on one of the dwarf galaxies discovered with DES gets back to this question of where do the heavy elements come from. So using very high resolution spectroscopy of stars in the dwarf galaxy Reticulum II, G et al. And later Roeder et al. Found that these stars, 7 of the 9 stars that were imaged that had high-resolution spectra taken in Reticulum II were found to be very R-process enriched, a factor of 2 orders of magnitude more R-process elements than other previously analyzed dwarf galaxies. And so while the star formation history and the total number of supernovae expected in this dwarf galaxy should be similar to that in other dwarf galaxies, it's possible that a single rare event could be responsible for this several order of magnitude increase in the abundance of R process elements. In fact, a single rare event becomes much more likely than a factor of 10 or more supernova than comparable dwarf galaxies. So these authors conclude that the existence of a R-processed enriched dwarf galaxy suggests that at least some of the R-process elements that we see today could have been created in very rare elements such as neutron-star mergers. Another very interesting observation that's come about and has gained a lot of attention in the literature recently is the fact that the distribution of galaxies, dwarf galaxy and dwarf galaxy candidates found in DES is not isotropic over the DES footprint. And in fact, if you divide the DES area in half, what you find is that 15 of the new satellites are in the southern half of the survey, which is the region that's closer to the Large Magellanic Cloud and the Large and Small Magellanic Clouds. So the idea is that the significance of this anisotropy is about 3 sigma, and the idea is that the LMC and SMC may actually be responsible for the anisotropy in the satellite distribution. So various groups have performed analyses asking how likely it is that the SMC and LMC could be contributing to the population of satellites discovered with DES. And various groups seem to be coming to similar conclusions that the Magellanic Clouds could be contributing about a third, maybe a bit less, between 20 and 30% of the dwarf galaxies that would be observed to be around the Milky Way. And the fact that DES is selectively observing close to the Magellanic Clouds means that it's likely that some of the satellites discovered with DES were at some time bound to the Magellanic Clouds. And from Jethwa et al., it seems most likely that they were originally satellites of the Large Magellanic Cloud that may still be bound or may have been recently stripped by the Milky Way as the Magellanic Clouds fell into the Milky Way potential. So now I'm going to move on to another, slightly a shift in topic, but another interesting regime of fundamental physics that dwarf galaxies contribute to heavily. So I mentioned before that one possible scenario for the microscopic nature of dark matter is that it could be composed of massive compact objects. Another that has gained a lot of popularity in the last several decades is that dark matter could actually be a new fundamental particle, which would be weakly interacting and massive. So the idea here is that dark matter may be composed of a particle that has the mass of roughly a silver or gold nucleus, so of order 100 GeV, so 100 proton masses. If this is the case, then these dark matter particles could annihilate, just like electrons and positrons annihilate, to produce other standard model particles, which could in turn produce gamma rays or neutrinos, which would be detectable here on Earth with various detectors that we have sensitive to high energy particles. Because the mass of the dark matter particle is expected to be of order 100 GeV, the idea is that the energy of these standard model particles would be of order several GeV. And for this reason, when we're looking for gamma rays, which are neutral particles that propagate to us uninhibited, we're interested in gamma ray energies of 1 to 100 GeV. So the idea is that if dark matter were to annihilate, this annihilation signal would trace the dark matter density, or rather the square of the dark matter density in the Milky Way. And so this means that the center of the Milky Way halo would be the strongest source, but the dark matter subclumps within which dwarf galaxies reside would also be very significant targets for searching for dark matter annihilation signals. So the Milky Way halo would have a larger signal, but also a larger background, while the Milky Way satellites would have lower statistics, but also much lower astrophysical backgrounds. So the instrument that's used to try and search for this gamma ray emission from dwarf galaxies is from this gamma ray emission both from dwarf galaxies and the center of the Milky Way halo is the Fermi Large Area Telescope. And so this is a paraproduction telescope that's sensitive to gamma rays in the range from a few hundred MeV to a few hundred GeV. So just to give you an idea of what the gamma ray sky looks like, so this is a map of smooth gamma ray photons above 100 MeV. Actually, sorry, above 1 GeV. And what you see here, the object actually in the center of this figure is Andromeda. And so you can see that the sky is not nearly as well resolved in gamma rays as it is in optical photons, but we are able to localize individual sources on the sky. And when you look at a map of spread across the Milky Way galaxy, what you see is that the plane of the Milky Way is very bright in gamma rays, and this is coming dominantly from the interaction of cosmic rays with gas and dust in the Milky Way, and that there are also a number of sources at higher latitudes. So the idea is that we want to try and extract some component of this gamma ray emission that could be attributed to dark matter annihilation, as opposed to these other more conventional astrophysical processes. So when looking at the galactic center, it's very appealing for dark matter searches because it's very rich in dark matter and it's relatively nearby. However, it's also very astrophysically complicated, coming directly from gamma ray emission from cosmic ray interactions with gas and dust, as well as a dense population of astrophysical sources, such as pulsars or supernova remnants, which are detected in other wavelengths and are expected to produce gamma rays. Nonetheless, when you try and model all of the astrophysical components of the gamma ray emission in the galactic center, what you find is that there is an excess component beyond all of the components that could be modeled astrophysically that is spatially extended and peaks at gamma ray energies of a few GeV. And this is exactly what you would expect from a dark matter annihilation signal, which should follow the dark matter profile of the Milky Way halo, which would lead to an extended morphology out to several degrees from the center of the Milky Way galaxy. And you would expect a peaked spectrum that would be related to the dark matter particle mass. However, you could also get this type of signature from a more extended population of millisecond pulsars or other astrophysical gamma ray emitters that are distributed at large radius from the center of the galaxy. So while you can go and interpret this excess in terms of a dark matter annihilation signal, which several groups have done, and which leads to interpret annihilation signal, what you find is a dark matter particle that has roughly the right annihilation cross-section to give you the relic dark matter density in the universe, and has a mass in the range of 10 to 100 GeV. And so this is very appealing. This is sort of exactly what you set out to find. This is the conventional, very conventional dark matter particle scenario. However, the galactic center is an extremely complicated region, and it's going to be nearly impossible to ever conclusively determine whether excess emission from the galactic center is astrophysical in origin or dark matter in origin. However, a dark matter signal should manifest itself in other regions as well, specifically in the dwarf galaxies. And so it's essential to search for this same signature in the dwarf galaxies. Because if we see the same signature in the center of the Milky Way and the dwarf galaxies, then it's a much stronger indicator that this could be a potential signature of dark matter annihilation. So we move back to this picture, and now we're moving away from the center of the galaxy and into the Milky Way satellites. And what you see here is a very different picture. So this is now gamma ray counts map centered on the Draco dwarf galaxy, and there is some low-level emission coming from extragalactic gamma rays, but this is a much cleaner target than the center of the Milky Way galaxy. And so this allows you to make up for the decreased amount of dark matter in the dwarf galaxies with an increased signal-to-noise ratio because you have a reduced background. Additionally, you have a very good handle on how much dark matter is present in the dwarf galaxies coming from measurements of the stellar velocities, where for the classical dwarf galaxies you have velocities for thousands of stars, whereas for the faint dwarf galaxies that have been discovered recently, you may have fewer than 100 stars and only tens of stars for the very recently discovered dwarf galaxies. However, this does give you a handle on how much dark matter is present and allows you to weight the individual dwarf galaxies both by their distance and their dark matter content. So when you do this, what you find is that there's no appreciable excess emission in gamma rays coming from the dwarf galaxies. And this allows you, and this is from 15 dwarf galaxies that were discovered prior to DES. And so this allows you to set constraints that are competitive with the dark matter annihilation hypothesis fit to the galactic center excess. They're not able to conclusively exclude that hypothesis yet, but they are in tension. And so that tension is relieved somewhat by the fact that we don't know exactly what the dark matter density is in the center of the Milky Way galaxy. So by adjusting the amount of dark matter in the center of the Milky Way, you can also adjust what cross-section you need to produce the galactic center excess. So again, what we're trying to do is actually take the sensitivity of the dwarf galaxies and increase it to a level at which modifications on the analysis of the galactic center excess and the amount of dark matter in the galactic center can no longer be used to escape a non-detection in dwarf galaxies. So in order to do this, we need more gamma ray data and more dwarf galaxies. And so this brings us back into the first half of the talk, where we tie in with the large number of dwarf galaxies and dwarf galaxy candidates that have been recently discovered. So the gamma ray data for all the new dwarf galaxies that have been discovered so far are already available because Fermi is an all-sky instrument. And we can look at 45 of the confirmed and candidate dwarf galaxies, and what we find is that 4 of these targets show about a 2 sigma local excess of gamma ray emission. Interestingly, 2 of these targets are very nearby, Reticulum 2 and Tucana 3, but some of the other dwarf galaxy candidates that have associated small excesses of gamma ray emission are much more distant and would not be expected to be strong dark matter signal contributors. So what we can conclude from analyzing not just these 4 dwarfs, but in fact the entire population of 45 confirmed and candidate dwarf spheroidals is that there's no significant gamma ray excess coming from the population of dwarf galaxies. However, in order to actually set the sensitivity to a dark matter annihilation signal, we need accurate dark matter mass measurements for each of these dwarf galaxy candidates. And so that brings us back to the problem that we were at before, where we need a lot of spectroscopy time in order to determine the radial velocities and the masses of the dwarf galaxies that have been recently discovered. But we believe that once that spectroscopy is available, if we're able to measure the dark matter content of the newly discovered satellites with equivalent accuracy to those that had been discovered in SDSS, we should be able to increase our sensitivity to a dark matter annihilation signal to the level at which we would be able to conclusively test a dark matter interpretation of the galactic center excess. So the summary from this section is that the dwarf galaxies are really essential for testing any dark matter hypothesis that's associated with an excess in the center of our galaxy. So just to wrap up, I'll mention briefly some of the future prospects. So with DES, there's a lot of unexplored territory when it comes to trying to find new dwarf galaxies. DES has just started the 4th year of its survey. In addition, a major reprocessing campaign is ongoing to improve the quality of the catalogs that were produced from the first 2 years, and in fact over all of the first 3 years of imaging. And this, combined with the added depth should allow us to be sensitive to fainter dwarf galaxies with larger angular sizes. So currently, it's unclear whether the locus of dwarf galaxies cuts off at low surface brightness because of some physical mechanism, or whether this is just a selection effect from our surveys. So DES should help us to push down into this previously unexplored territory of very low surface brightness objects to try and help answer this question. Additionally, we've begun to use DECam outside of the DES footprint to get more contiguous imaging around the Magellanic Clouds. So this is as part of an NOAO community survey called the Magellanic Satellites survey, where we're now imaging about 1,200 square degrees around the opposite side of the Magellanic Clouds from DES. And so this should allow us to test the Magellanic origin of the satellites that are being discovered in this part of the sky. We expect to be able to discover of order 10 new dwarfs in this area of sky if the hypothesis that these are dwarf galaxies originally bound to the Magellanic Clouds is actually true. Finally, there's a lot of DECam data that's out there that's outside of the Dark Energy Survey or the Magellanic Satellite Survey. And it should be possible to use this collection of deep imaging data to actually cover all of the southern hemisphere at a depth that is comparable to or deeper than Sloan. This map was from earlier this year, and it's getting filled in every night that DECam is on the sky. Finally, on the longer term, the Large Synoptic Survey Telescope, LSST, is coming along in the next 5 to 10 years, and LSST will take another extreme step forward in sensitivity, pushing down another 2 orders of magnitude in sensitivity, and should allow us to have a complete census over the southern sky for ultra-faint dwarf galaxies out to the virial radius of the Milky Way. So this should allow us to very conclusively test the missing satellites problem. So if our understanding of how galaxies form and the dark matter distribution around the Milky Way is correct, we should find of order 200 to 300 dwarf galaxies in LSST. And so what we project is that over the next 10 to 20 years, that DECam and other southern sky surveys will discover a handful, perhaps doubling again the number of satellite galaxies that we know of, and then LSST will come along and contribute hundreds of dwarf galaxies to the virial radius. So in conclusion, ultra-faint dwarf galaxies, just to emphasize again, are some of the most numerous ancient and chemically pristine and dark matter dominated galaxies, which as extreme objects makes them excellent probes of fundamental physics. However, due to their low luminosity, our census of dwarf galaxies is far from complete. And that was made blatantly obvious over the last year with the massive number of dwarf galaxies and dwarf galaxy candidates discovered by DES and other surveys, and should continue. This trend of rapid dwarf galaxy discovery should continue over the next 2 decades with LSST coming online to help us probe really out, to really help complete our census of Milky Way satellites. So that's all I have, and thank you for your attention. Sorry for running a bit long.
Okay, thank you very much. Very nice talk. We have time for questions.
Okay, this is Basilio. Hi, Alex. Thank you very much for this nice talk. Can you hear me well?
Yes, I can hear you, Basilio.
Okay, great. How primordial do we expect these very low luminosity dwarf galaxies being found to be? I mean, isn't there a possibility that a fraction of them could have formed not from primordial perturbations from the early universe, but formed later on, and perhaps not being so dark matter rich, like tidal dwarfs, for instance. And I think this question connects a little bit to the very bottom of that luminosity versus size diagram, where we do that clusters which do not have dark matter are quite distant from the dwarfs when in the bottom, in the upper part of the diagram, but that's the one. But as you move towards lower luminosities, these two start to mix up. So what is going on there? Are these all dark matter rich, the ones with low luminosity, or do we expect to find things that clearly are not?
Yeah, so those are both really, really great open questions in this field right now. So on one hand, as you push down to lower surface brightness, so into this regime where we don't have much data, eventually you get to the regime where you're looking at objects that would more conventionally be called stellar clouds, right, or very diffusive streams, right, where you're covering subtending a very large angle on the sky with relatively few stars. And so, yeah, objects like this could arise either from tidal interactions, as you suggested, or from the disruption of dwarf galaxies as they get tidally disrupted by the Milky Way. And so I think at this point we have N-body simulations which we think can give us a predicted number of dark matter-dominated objects, but we don't have a comparable, clear framework for predicting the expected number of baryonically produced or tidally produced satellites. And so I think that's exactly right. The two regions of this plot where we're going to learn a lot in the next few years are going to be the region right in between the globular clusters and the dwarf galaxy locus at low luminosity, and the region at very low surface brightness, where you're starting to hit the boundary with stellar clouds.
Okay, more questions?
Well, if nobody asks questions, I always have questions. So here's the second one, Alex. If 30% of the satellites on the southern half of the DS footprint are native to the clouds, you are still left with a significant asymmetry in the sense that you have, say, 2 dwarfs in the northern part, and you're left with 10 dwarfs that are likely to be native in the southern part. Isn't that worrying? Where would they come from?
So sorry, I think I went a little too fast here. So the idea is that this is 30% of all satellites within the Milky Way virial radius. So this is 30% of the satellites integrated over the entire sky. And so within the DES footprint, as predicted by, say, Jethwa, they predict that somewhere around 10 of the satellites within DES could be attributed to the Magellanic Clouds in origin, 10 to 11. Yeah, and so clearly this is an anisotropic distribution but integrated over the entire sky at DES depth, you expect there to be of order 100 satellites, and that 30 of them over the entire sky would have come from the Magellanic Clouds.
Okay, fine.
So I would like to know how the constraints on dark matter mass and cross-section compare to Earth-based detectors.
Yeah, okay, so that's a great question. So there are a few complementary probes that I'm going to give you one answer that may be satisfactory and one answer that will not be satisfactory. So there are various techniques for trying to detect dark matter. One of those is to build very sensitive detectors, to bury them deep underground in mine shafts usually, and to wait for the very rare occurrence of a dark matter particle scattering off of a nucleus, an atomic nucleus, and depositing a little bit of energy into your detector. Unfortunately, the process that leads to WIMP nucleus scattering, so dark matter nucleus scattering, is not the same particle physics process that leads to dark matter annihilation. And so you would have to imagine that there's a third axis on this plot, which is the scattering cross-section, which is where these Earth-based direct detection experiments are probing. And so it's possible to have dark matter models that would be detected both by the gamma ray observations and the direct detection experiments. But it's also possible to have models that would be detected by one but not the other. And so all of this is dependent on the exact particle characteristics of the dark matter particle. So the answer is that in some cases they are competitive and they're probing the same space of models. In some cases they're probing very independent types of dark matter.
Okay, thanks. And I'd like to know if it would be possible to detect these dwarf galaxies around other nearby galaxies, big galaxies.
Sorry, I couldn't hear that.
I'd like to know if it will be possible to detect dwarf galaxies around other big nearby galaxies in the future.
Yeah, that's another really great open area of investigation. So there have been several articles that have come out recently detecting classical dwarf galaxy analogs. So these are the kind of dwarf galaxies that were being discovered before Sloan around field galaxies that have masses maybe similar to the Magellanic Clouds. Around Andromeda, we know that there is a very active satellite population. Again, we're probing them at brightnesses that are similar to the brightest dwarf galaxies around the Milky Way. We're not probing the regime, these ultra-faint galaxy regime that we can do locally. But yes, we can test a lot of the same hypotheses about lambda cold dark matter by looking at nearby galaxies as we can around the Milky Way. The problem is we just can't get as faint as we can around the Milky Way.
Okay, thanks. Questions? More questions? Okay, so I want to thank you, Alex, again. Very nice talk. And thanks everybody for coming, and see you all soon.